square root and get value of m. So get value of m quickly, please. So
Uh,
what's the answer?
I think I got 16.19.
Okay, so I have to put here another bracket and it is 16.9. Okay,
One.
16.19 and obviously it is meter minus 1. So that's okay. Now the next step is to calculate LC. So LC equal L plus thickness over 2. So can you kindly get this value? So L is 0.05 meter, which is 50 millimeter mean, uh, 0.05, is it right? Plus T by 2, which is 0.005 divided by 2. Can you calculate how much is LC?
I got a 0.0525. 05.
0.0525. Okay, this is in meters, obviously. Okay, next is area, fin area. So what is the fin area? Fin area is 2 multiplied by width multiplied by characteristic length. So how much this gets? So it is 2 multiplied by width is 0.1 and multiplied by LC, which is 0.0525. So how much we get this one?
0.0105.
0.05, which is meter square. Okay, so this is your all the values. Now you can calculate efficiency. So now you calculate efficiency. So efficiency is equal to tan hyperbolic MLC divided by MLC. So go to your calculator and make sure that you have LC, you have M. Remember that you cannot cancel M by M or LC by LC because in the numerator you have tangent hyperbolic of that value. So take the tangent hyperbolic of that value and then divided by this product. So please do that. So
I got
0.813 then
yeah,
basically.
I got the same thing.
Yeah, so which is basically 83.1%, right? Okay, then the second thing is that second, so this is first answer that they say what is, then they say what is the heat transfer rate? Well, you should know what heat transfer rate is. So you know it's a Q dot. So Q dot, ideally Q dot, when we see the Q dot is usually given by Newton's law because it's all convection. But obviously it should be H area of fin multiplied by TB by T infinity, base temperature minus infinity. But we multiply it by the efficiency of the fin because if we put Q dot without efficiency, then it simply assumes that it is 100% efficient. And it is not. In our case, it's 0.83. So you have to put the values there and you have to multiply it. So 0.813, which is the efficiency, multiplied by H, which is 154, multiplied by area of fin, which you have just calculated 0.01525, and multiplied by this bracket, which is basically 350 degrees centigrade minus 25 degrees centigrade. Air is at 25 degrees centigrade. So this is a very straightforward calculation. Tell me what is Q dot.
620.53
Yeah, 600,
and 20.5.
600. Oh, this is wrong probably.
Oh,
It's 0.0105. 0.0105. Sorry, I just put the wrong value. Okay, now you tell me. Oh, 427.25. That is really good. That is in watts. Now the next step is he's saying find fin effectiveness. So we will go fin effectiveness, which is epsilon, which is epsilon. And in that case, the formula is again given in the book. You should have that formula here. Remember that we put two formulas there, and these relationships are important. Uh, Basically, your fin efficiency is Q dot over H area of base. Remember, this is the area of the fin when you put Q dot. When you calculate the fin effectiveness, this area is the area of the base. So, and area of base is obviously base is W multiplied, which is width multiplied by the thickness. This is the area of the base here. Base is at 350 degrees centigrade. So this is the area of the base, which is this one. It's a rectangular fin. So obviously it is same here and here. So area of base will be W into T. It is the area of this front surface. And that is on the back, it's exactly the same. So important thing is that you must put the values. Now, can you put the values there and can find out what is the fin effectiveness? So it is 17.07. Okay, so that's basically what we have to do in this question. Remember that this question really depends on what kind of fin you have. Obviously, if you look at if you look at, some other fins, right, which are pin fins and all those. Now these fins, uh, these if you get different fins, then you have different kind of relationships. Then effectiveness is not tangent over tangent. They are the Bessel functions I2 ml and I1 to ml. So the I2. So you have to look at those efficiencies. M is different from each case. So I think one question we did in the class, which was the blunt, this guy, which is a pin fin of the parabolic profile, and there was a blunt profile somewhere. So these are the value of M. This is the area. Two things will be given: area and value of M, because we will use M everywhere, and efficiency. And once you have, you can get a Q dot from the formula, and also formula will not change, and you will get also after Q dot, you will get some other values, right? For example, the field effectiveness. This is amazing. Let me check that. So, no, one should be I0. Yeah. So that is actually, we solved this question, right? It's in the book. So let me check that. Let me check that question because I remember solving it in the class. And we calculate I0, I1. Yeah. So blunt, it was blunt one, right? Yeah, I don't think it is I1 both places. This is a mistake. It should be let me check that question, and then there was a question where I calculated the I values. Which one was that? Table 3.
There is a
So
pin.
I1 over I0, I believe. I1 over I0.
Well, there's one for a triangular profile down lower, and it's I0 over I1.
Yeah. Where is that one?
The I0 over I1, that is pin fins with triangular profile.
Yeah. That is, I think that we still do the same here as well. Because otherwise they will be cancelled and you only get 1 over ml. That is not right. Okay. Yeah, that is not right. All right. So let us now do another question, which is a good question as well. And you will, so here is the print screen, and I will do this question for you here. So this is another, and here is, so 121 is also a very good question. So you can see that. Okay, so the turbine blade made of a metal alloy, K value is given as a length of 5.3 centimeter. So length is given, cross-sectional area is given and perimeter is given. The turbine blade is exposed to a hot gas from the combustion chamber of 973 degrees centigrade, and a convective heat transfer coefficient is very high, is 538. The base of the turbine blade maintains a constant temperature, right? And determine the heat transfer due to turbine blade and temperature at the tip. So we have to find out the temperature at the tip, and we have to find out the Q dot. So what do you think is the way to solve this question? Obviously, first thing I will urge you to understand the question, and you understand that what actually we want to do. So I believe that you can treat this blade, first of all, uh, because the tip is so small and it is very uh, uh, normal really uh, to put the turbine blade really as a here. So this is very traditional and this is common way to solve these turbine blade problems. So they will be treated as a uniform cross-section fins with a, because it's little bit bent, but they will say that they are uniform cross-section fin and adiabatic tip with adiabatic tip. So the heat transfer rate will be from the adiabatic equation, which is HPKAC T infinity minus TB tangent hyperbolic ML. So this is the value which you will get from the adiabatic tip. If you go to your, let me go to your adiabatic tip. Let me go here. Question number 5. So adiabatic fin tip, special temperature, adiabatic fin tip. Yeah. So if you go to your, there are efficiencies and these things are given here, right? If you go to your, at the end of the chapter, you will get that, and adiabatic fin is given by this equation HPKAC minus T infinity tan hyperbolic ML. So all the formulas are given, but you have to choose the correct formula. So what I will feel that now you should be able to find out, first of all, ML, because ML is important, and ML is given by this equation. ML is given by this equation because, so M, you already know M, which is HP over KAC square root, because it says it says square is this case where M is 2H over KT. Is it 2H over KT? No, HP over KC. Which one is this? Rectangular fin tip. So 2H over KT here. 2H over KT. But why they are getting PH? Let me check this value. So thickness over, so let's go back to here. I think in these equations there is a value of, let me find out that for you. Hold on, let me check where it is. So HP, so this is the area of cross section, and the area of cross section is KP over AC. So AC is inside HPKC. There should be a formula somewhere. Why they are saying HP over KAC, HP over KAC, adiabatic fin with, just give me 1 minute, I have to find out the value of M. So 2H over HP over, okay, so this is the parameter which is given. I found it here. Yeah. So for very long fin or for other, so you have to look at, I'll put it here for your here. So they will say here specific fin, specified temperature and fin tip, convection from fin tip. M in each case is HP over KAC, where P is the perimeter, AC is the cross section, and then the Q dot can be found with various fins. Long fin is this formula, for adiabatic fin tip is this formula. So in each case, the M is HP over KAC, which is given here in this line here. So we use that. So M is HP over KAC and L is L. So why don't you put the values and tell me what is the answer for ML? Because we calculate ML because ML is given basically, ML is given in each, well, let me floating. So MH is given for each, uh, you know, 10 hyperbolic ml, so we are calculating ml. You can calculate m separately and multiply it with L. So why don't we do that now? So it will be square root, and you write the value of HP over Kc. So it is 538 HP. Perimeter is given 0.11 because it is centimeters. So perimeter is given here. P is equal to 11 centimeter divided by K, which was small value 17 watts per meter C, multiplied by, and this is in denominator. So we put another bracket here, divided by AC. Area of cross section is 5.13 centimeters square. So it is 5.13 e power minus 4. And this is your value of this one multiplied by L, which is the length of this is given uh, 5.3 centimeter, which is 0.053. So all these values are given here. So can you calculate what is ml?
I got 4.36.
Yeah, 4.36. So this is your, oh, I'm writing. So it is 4.36. So if you get this value, then you can calculate really, you need also to calculate HPK square root because this is the coefficient. So why don't we find out also square root of HPKA? So HP, so can you calculate that? HPKAC, can you calculate that? All the values are already here. Right? H multiplied by P perimeter multiplied by K thermal conductivity multiplied by area of cross section and square root. So tell me what is the value?
Is it 0.718?
Okay, so if this is done, so you can Q dot you can calculate. So Q dot will be equal to 0.718 multiplied by T infinity minus TB. So T infinity minus T base, which is 450, and multiplied by 10 hyperbolic ml, which is ml is given is 4.36. Just calculated that. So please calculate this.
I got a 375.6.
375.6 watts, and that's what was being asked. Now the next question, which the next part is that find out the tip temperature. So which means TL, temperature at tip, tip temperature. Now you have to go back. Uh, you have to go back to your book and find the tip temperature. So tip temperature for adiabatic fin tip is here. Adiabatic fin tip is this temperature. So basically this is the temperature. Adiabatic fin tip temperature is this one. So I will say here fin tip temperature is this one. So can you calculate from here Tx? So T, first of all, it is cosine hyperbolic and that. So find Tx is basically TL. Okay. Uh, so remember that we need to calculate temperature at X is equal to L. That is the tip temperature, right? So we have to calculate that. So how will we do that? So I should say here that fin, these are the note that the fin temperature is obtained at X equal L. If that is the case, then your TL, T at L will be equal to, so look at this, L minus X mean L minus L is 0, cos 0 is 1. So TB minus T infinity will go on the top. So it will be, it will be TB minus T infinity. So I will get this bracket and I will get TB minus T infinity, right, divided by cosine hyperbolic ML. And so this is, right, this is one term plus T infinity, which is this one. This will go on the other side. It will become T infinity. Now you use the values here. You have all the values here. Your TB is, so you have 450 minus TB minus T infinity. So that is 973, right, divided by cosine hyperbolic ML was how much? 4.36? 4.36. This is your ML. And when you calculate that, then you say plus T infinity, which is 973. So tell me how much your answer. What is the answer?
I got a 24.756.
That looks huge. The
Okay.
point tip temperature can't be that huge. So this is basically, this is your TB. This is the base temperature, TB. TB minus T infinity. So remember that you calculate this first and then you add 973. T infinity is 973, right? No. Yeah. It should be very, actually the first one should be small value because it's divided by cos hyperbolic, which is, so, and this is very small here. So what is the value you get?
I got 960.
960. Well, 960 is probably
I got 960.
Yeah, okay. So this is basically your question. So In these two questions, which is important thing to see is that uh, if I give you this question, I will tell you this one, that you can treat it as a uniform cross-section fin with adiabatic tip, so that you can go to these tables and find out the proper values of temperature ratios, and also you get that value of Q dot, which is roughly somewhere here. So uh, information will be fully given. Uh, Half information cannot solve question. So let's do another question. So do you have any reservations on these? What two examples we have done? They are very important examples, as I feel and I see them. So let's do another question, which I believe is good. I gave one question to you. Hold on. I gave one question to you, which was, ah, uh, that's a good question, actually. Let me give you this question and see how you can solve it. You probably need a calculator or something for this, but let's do this question. Okay, so can we read this question? A 50-meter long cross section, long section of a steam pipe. This is a steam pipe. It is 50-meter long, whose outer diameter is 10 centimeters. So outer diameter is 10 centimeter here. And to an open space at 15 degrees centigrade. The average temperature of the outer surface of the pipe is 150 degrees. So this is the outer surface of the pipe is 150 degree. If the combined heat transfer coefficient is 20, determine the rate of heat loss from the steam pipe. B, annual cost of this energy. C, the thickness of the fiberglass needed to in order to save 90% of the heat lost. And assume the pipe temperature remains constant at 105. So the pipe temperature remains really constant, uh, right? And we have to put the fiberglass insulation there. Assume the pipe temperature to remain constant at 150 degrees centigrade, sorry, not 105. So this temperature remains constant when you put the fiberglass insulation. So how you will tackle this question? So you have to tell me how you will do what you need really to find out the first part. So what is the first part? How you will tackle this question? So let's do together and see how we will do that. Everything is given to you. There is nothing there which is not, which is basically is difficult, right? So let's do that. Let's do this question. So basically, Q dot for the cylinder should be the surface area, right? Newton's law, right? So Newton's cooling law. So the solution is for Q dot, use Newton's law of cooling. Okay, so use that. So Q dot basically is equal to H area, right? This is our basic formula, which we already know, right? Remember that A is the surface area of the pipe. Surface area of the pipe. And surface area of the pipe will be is equal to, right, circumference 2 pi r, which is the radius, right, multiplied by the length of the pipe. right? So this is the surface area of the pipe, the curved surface of area. So you get the circumference of the pipe for the outer radius, and that circumference multiplied by length, which is 50, will give you the surface area. It's not area of cross section. So can you calculate that, please? 2 pi multiplied by r, which is 0.1 meter, multiplied by 50 meter, which multiplied by 50 as usual. So what you get?
Uh, 31.41.
31.41. Now can you put it in Q dot? So Q dot will be equal to H is 20 multiplied by surface area, as you said, 31.41, multiplied by bracket T surface. We see that the surface temperature we keep surface temperature we keep 150, okay, and minus it is open to air at 15 degrees centigrade. Now I want to ask you one thing. 2 pi r, well, this is not r, it should be 0.05 then, because I get 2 here. That was the diameter, so it should be half of that. Can you redo the calculation?
Yeah, it's just half at 15.7.
Yeah, 15.7. Yeah, you're right. Yeah, 15.7. And that 15.7 will go here. Okay. And because they are just simple subtraction of temperature, so you do not do really. So this is the, okay, so what is the value?
I'm not sure. I got 42,411.
Yeah, 42,400.
411.5. Yeah.
Watts. Okay. Now, the next question is, what is the heat loss? So heat loss per year. Well, that is not difficult, really. It is Q dot, what you have, multiplied by delta T. So per year mean 365 days multiplied by 24, so total hours multiplied by 3600, right? So how many kilojoule per year you get? So calculate that. So give it in not joules, kilojoules. So you divide by 1000 and then tell me per year how many kilojoules. It should be 1 point something e power.
Before dividing by 1,000, I got 1.34 to the 12.
1.34 e power.
12.
No,
No.
it should
Well,
be
so that was then to divide it by 1,000. It's 1.3 to the, what's that?
9
9. Yeah.
plus 9. Yeah, kilojoule per year. So that is the heat loss, right? So straightforward. What was the so if we have the, we want to find out the, about the combustion, gas combustion. So for the furnace, so if the is any efficiency is given, so you have to calculate in therm, which is 105,500 kilojoule, because the price is given in thermal. So $0.52 per therm. So 75%, the natural furnace has the efficiency of 75% and price is given to this. So it simply means that we have to convert the Q gas into therm per year. So Q gas, so we will say uh, gas consumption, gas consumption, gas consumption from the natural gas, natural gas furnace. That will be equal to, very simple, Q, not Q dot, Q. Heat loss is actually Q equal to, sorry, capital Q. So that will be Q, whatever the kilojoule, then you multiply by its efficiency, right? So which is the kilojoule per year. So you divide it by whatever the unit is, kilojoule. One therm is 105, 105, comma 500. Is it comma 500? Right? So go back to the question and look at that. It is 105, 500. So 105, 500 and multiplied by 0.75, which is your efficiency. So can you calculate this, what the value is? How many therms per year you get?
Is it 16,903 point?
16,903 therms per year. And now the cost can be given. So the cost will be dollar amount, therms, which are 16903 multiplied by the dollar. That is $0.52. So how much it becomes? How many dollar per year? That is the expense of the gas.
8,789.82.
So that much is the money which you will give per year. Okay. Now, what is the next part? The next part is that the thickness of the fiber insulation is this one in order to save 90% of the heat lost. So 90% of the heat loss we have to find out. Okay. So we have to see that we have to find out our Q bar and multiply it by 90%. He's saying that the thickness of the 90% of the heat loss we have to save. So 10% will be, basically 10% will be our the 10% will be lost, basically 90% will be saved. So we have to see the loss here, loss with 90% reduction, with 90% heat loss reduction. That will be equal to whatever our Q was, Q dot. It will be whatever our Q dot was, you multiply it by 10%, which is 0.01. So this will be 424,115, 11.5. So 424,241,1.5, right, multiplied by 0.1. Okay, so what do you get? So it will be 42, 41, right? 42, 41, roughly. So it will be 42, 41.0 watt. It's approximately. So this is our, that much is our loss. And now we have to find out the insulation, Q dot insulation. So for Q dot insulation, if you have not forgotten, so we have to find out the Q dot insulation. So Q dot insulation, that we have to find out. Now you remember that the resistance model for this one will be R insulation and R0, which is and T air, and then you have TS. So it start with the TS surface temperature, then you have insulation, then you have RO, and then you have T air. So you remember that Q dot insulation, if you go back to your chapter, right, this will be equal to, this should be equal to this. So this is also the formula given. You do not need to prove anything. It should be end temperature difference from left to right, Ts minus T air, divided by the resistance, right, of the pipe to the heat transfer plus the R for insulation. Now R is 1 over H0 A0, and R for insulation, because it radius, it will be log R2 over R1 over 2 pi KL. This is the formula for R for cylinder. If it would be a slab, this R insulation will be, do you remember what it will be? It will be LK over something, right? So that formula is different when it is. So now you put everything in it, and you should be able to get the value of R2, right? So it's a little bit tricky because you have to calculate the R2. The problem is that R2 will appear here as well. This is the surface area. So I tell you now one thing, that A0 is the surface area, and that will be equal to 2 pi R2, right? This is the surface area, circumference, multiplied by your length. So this is your area, surface area. Now R2 is here as well, and R2 is here as well. So I will just say that because R2 appears in two terms, on the right hand side, right? We need calculator to equate left hand side with right hand side by choosing different values of R2, by choosing different values of R2 and minimize the difference between left hand side and right hand side value, right? Values. So in that case, really you substitute in this equation, you will get, by using your calculator, you should get that. R2 should appear, and then you can calculate the thickness of the, now you have R1 value, you have R2 value. So thickness of the shield, or thickness of the insulation will be equal to R2 minus R1. You have both values, and your answer will be approximately 1.92 centimeters. So that much is required. So this is a slightly difficult question. The first part is very simple. H0 area Ts minus T air. Just remember that area is the surface area. This is one thing. Then heat loss per year is also very simple in kilojoule per year. You can divide it by 10550 and multiply it by efficiency. So that will be your gas consumption. And then one question here you can say why this efficiency is not on the top. It's on the bottom because we need more, right? Right? We need more gas consumption to make that the further reduction of that much efficiency. So it is 0.75 is divided, not multiplying, because we are looking at the gas consumption rather than the efficiency of the, right? So because I think it's a furnace efficiency is there, so it needs more gas basically. And that's we got it here by dividing. So you get in therms per year, and cost is given per therm is $0.52. That's very easy. Then he's saying that we want to avoid the 90% loss reduction. We want to achieve that, and we want to avoid loss. So it simply means that whatever Q dot is, only 10% of that should go away. So that many watts will go away. If we keep the insulation, then of course you do the model for insulation and RO for the pipe, then it will be this difference divided by the total resistance. And total resistance for R0 is 1 over H0 is 0. And for the insulation between R1 and R2, it will be log of R2 over R1 divided by 2 pi KL. All the values are given. Q dot insulated, we just said it is 4241. These are the temperatures constant because it says that the temperature 150, assume the pipe temperature remains constant. So it is always 150 minus 15 divided by 1 over H naught is 20. Area is 2 pi R250 L, which is L. Log R2 over R1 is 0.05. Divided by 2 pi KL, everything is given. Now you use your calculator to put different values of R2s and see that if left hand side becomes the right hand side. That particular value of R is 0.0692. You may be close, you may be say 0.07, or you can get nearest value, and then you can divide to get the insulation thickness. Is this question clear?
I know, yeah. Complicated.
This is a good question, and remember that these are not difficult questions. It's just they look difficult, but if you carefully look at those, they are not difficult questions. So this is question 3. Let me do question 4. And I'm writing the, okay, now let's do another question, which is, let me find out that question. I saw it here somewhere. Oh God, where is that? Just give me 1 second. I'm just looking. Some very simple question which you can really do properly and understand. So I want to give a very simple question to you. Okay, so this is a good question. And this question I have given in the assignment as well. So you can do that and you should be able to really. So this is the wall. Actually, we did it in the class as well, but obviously, so this is a foam, then you have a plaster, then you have brick. And the thicknesses of the plaster and this area where the brick is, and then the brick width, and this is given. So 4 meter high, this whole wall is 4 meter high, 6 meter wide, and this width is 6 meter. Consists of long 18 centimeter by 30 centimeter cross section of horizontal bricks. So bricks are 0.72, separated by 3 centimeter plaster. This one is 3 centimeter, 3 centimeter. Plaster K is given, and 2 centimeter grid foam, which is this one, 2 centimeter. And then it's saying the indoor and outdoor temperatures are given. Convective heat transfer coefficient is given. Assume one-dimensional heat transfer and disregarding the radiation, determine the rate of heat transfer through the wall. Now, obviously, this question needs very simple. This question needs your the this question needs the model equation, right? So let's make the model first. And I will not ask you to solve it, but you can solve it, but I can explain to you the solution. So here it is. So you start with T infinity 1, then you get Ri, then you get R1, then you get R2, and then you have R3, R4, R5, then you have R6 and an R7 outside, and then T infinity 2. So there are three. So R1, Ri is here, where the temperature T infinity 1, and then you have the convective R resistance. Then you come in the blue foam, you get R1. Then you go to this thickness of 2 centimeter. Then you get R2 there. Then you have three things. You have this plaster, brick plaster. So I will put here R3, R4, R5. Then next one is again plaster of 2 centimeter, which is R6. And then you have R7, which is outside, and then you have T infinity 2. Do you understand the resistance model here? I mean, do you have any question on that?
Could you explain where the RI, which section that is?
Yeah, I will. So T infinity 1 is here, right? So T infinity 1 is here, right? Why it is not listening to me? So
Oh wait, never mind. I understand it. Never mind.
this is T infinity here,
Right.
right? And T infinity 2 is here. So T infinity 1 and the blue wall here on the foam, that will be the convective heat transfer, which is R1.
Okay. Thank you.
Ri.
Yeah.
And R7 is outside, right? R7 is outside. So you have T infinity temperature here, right? And you have then R1, then you have blue one, which is R2, R1, sorry, that is Ri, then R1, then R2, then three of them are in parallel, which is R3, R4, R5. Then you have R6, which is 2 centimeter. Then you have R7, which is outside the wall, inside the room basically. And then you have T infinity 2, which is the room temperature. Okay, 22 degrees centigrade.
Okay.
And
Thank you.
T infinity 1. So is it clear?
Yeah, I understand now.
Okay, very good. So now you will see that if that is the case, right? If that is the case, then you have to calculate all R's. You have to calculate R1, R, RI, R1, R2, R3, R4, and then you sum them. So I will just give you the solution here that Ri is R convection 1 over H1, HIA. H1 is 10 watt per meter square, and A area is given. Remember, one meter width and 0.33 meter. So it says somewhere here, it has a value 3 centimeter. This is 18 centimeter long. Oh, 4 meter high, 6 meter wide. Right, this is a 4 meter high, 6 meter wide. So that width is given like this. It's not shown, but it is like this. So basically you have the area, right, per unit area. So just multiplied by length, width, and then you get these values R1. R1 will be L over Ka because it's pure conduction. L is given 2, L is given 2 centimeter here. Area doesn't change. So thermal conductivity is given, area is again 0.33 multiplied by 1. So you get R1. R2 is same, plaster, L over Ka. L is given for plaster, the blue thing is also 2. So you multiply it by 2 and then keep working on those. And then for 3, 4, 5, they are parallel. So you have 1 over R mid is 1 over R3, 1 over R4, 1 over R5. Get the value of R mid. And then you add all of resistances to get the total resistance. Once you have total resistance, then it is very easy because then the steady state, then you have the steady state rate, then you have the uh, then you have Q dot is T infinity 1 minus T infinity 2. Now remember, people make mistake that inner temperature is minus 4 degrees centigrade. So you must have T infinity minus then another minus 4 because T infinity 2 is minus 4 degrees centigrade. So this is very important that you put here minus minus, it will become plus. If you put 4 and use this minus as minus 4 degrees centigrade, that will be a disaster because you will get wrong value. So you get Q dot, and then through the wall, which is 4 meter per 6 meter cube volume over your area, that will be the total Q dot through the wall, which is 456. So this value multiplied by the total area of the wall divided by, this is a basically the ratio here, right, which is area total length is 4 by 3, I think, 4 by 6, 4 by 3. So it is 4 meter high, 6 inch wide. So the total will be how much? Total will be 24. But then we already this value 6.23 is for 0.33 meter square. That is the area of this one. So this is 30 multiplied plus 1.5, 1.3. So it is 33 centimeter. And it should be 18, 20, 24, 26. So 30 multiplied by 26. So if you do that, you will get your 0.33 meters square. So you have to divide the total area by this one because this Q dot is for 0.33 meters square. That is why we are dividing the total available area by 0.33 because 6.23 watt passes through that area, which is per unit area, per this area. So that's why we get 456. So this is the total Q dot. Is it clear? Do you have any question which you don't understand? This is important question, by the way. This question is important because it tells that whether you can calculate these values. So this is important, that where this 0.33 is coming. So this is very important for you to understand that this is 30 centimeter. This is 1.5, 1.5 is 3. So 33 centimeter divided by 100 is 0.33. So this is per unit length. So you will get multiplied by 1. So that's why 0.33, 0.1, 0.331 is common for the area. This is the area in which we are calculating the brick, the side black plasters and the foam. And these two vertical and horizontal line is the one in which the calculation is being done. And that area is, length multiplied by width. So length is 0.33, width is per unit. So that's why it is 0.33 multiplied by 1 everywhere. And when you go for R3, R5, so you make sure that your areas are correct. The areas has to be correct. So you should be very careful in putting the areas. You have to look which area you are looking. For brick, you are only looking 0.3 centimeter, so 0.3 meter. And for this one, you are looking for probably 31.5 somewhere. So you have to look at those very carefully, which area you are considering and how much is that area. That is basically whatever the height is, multiply or length is multiplied by unit width. So then you calculate that, then you put in this equation. Make sure you put -4 separately here to make the overall thing plus. And then you have also the Q dot total. Total area is 4 meter high, 6 meter wide, 24 meter square. But the calculation was done for 0.33. So you need to divide it so that you get the correct ratio, and you multiply it by 450. You calculate it is 456. Do you understand that? Do you understand this question?
Yes.
These are question 5. I will say this probably will be the last thing I want to do. Question 5 is the derivations. The derivation basically in this case, please see plane wall and cylinder, plane wall and cylinder, Q dot equations, how you derive them. Also, I want you to look at plane wall and cylinder models, which you have just done. This model, this is for the plane wall, but for circle, we have used it here. This is for the circle, log R2 over R1 2 pi LK 1 over this. So make sure that these two things were derived in the class. So I would like you to really carefully look at that. Apart from that, please revise chapter 2 questions given as homework. Just revise those little bit. Homework questions, okay? So I think if you do this work properly, you should be able to get your, let me save it. You should be able to go over this quiz midterm very easily, okay? So I tried to do some basic questions with you, and I will put this inside my file section. This is called Special Session 2, ME114, March 19. So do these questions again before you come to the examination. You have tonight and you have tomorrow full day because your exam will be at 3 o'clock. So you have a lot of time. So look at those and look at the questions which we have done. Try to do some questions which we did in the class. So I think you should be okay to to go through this exam easily. Do you have any question? Which assumptions? You just solve it. I mean. Yeah, but if I ask you to derive something, then obviously you have to tell me why this equation is so simple. Right? So I can ask you, hey, this is the equation, 1D equation in plane wall, rectangular. Why it is so simple? Then you have to answer. And why is so simple? I'll ask you compare this equation with the general equation and tell me why this is so simple, right? So you have to answer those, right? So this type of conceptual question, one question might be one part might appear like this. That will test whether you understand the equation itself and you understand why it is so simple. What were the assumptions? Okay. So do you have any other question? Well, if not, then please prepare these questions and prepare derivations, which I said. And thank you so much for coming and working hard. Thank you. Okay.
Thank you. Bye.